Okay, so let's see. So where we left off was we had that the scattering length was equal to minus delta tangent alpha over alpha minus 1. And we showed that there were almost bound states of A is negative and large, and there are barely bound states of A is positive and large. So let's see. So let's say that A is not large. Let's continue that example. And then our scattering amplitude is 4 pi over m, 1 over k cotangent delta minus ik, which goes as k goes to 0 as, and we'll say that, so I should have, this was our picture of A versus alpha. And so for generic alphas, so namely not in this very narrow region around these points where there's a bound state in the potential, but for most regions here, what you find is that this is A over delta here, that A over delta is order 1 is generic. So if you don't fine tune your alpha to have these bound states, then typically A over alpha over delta is order 1, which means that A is order delta, which is what I would call 1 over the UV cutoff by definition. So therefore, as k goes to 0, this goes to 4 pi over m, 1 over minus plus or minus 1 over delta, sorry, 1 over lambda. Sorry. So this is minus 1 over A, which is on the order of plus or minus 4 pi over m lambda. Now, that means that the cross section is proportional to the amplitude squared. This goes like 1 over lambda squared. But the question is that big or small? Well, we can define a dimensionless cross section by writing it as sigma k squared, where k is the wavelength, k inverse is the wavelength of the experiment we're working at. So this is the IR scale. Which is the lab scale. We're doing an experiment. And so this is a statement. I want to look at the cross-section in units of the only scale that I've got in tuning in my experiment here. So if we do that, then we find that sigma hat goes like k squared over lambda squared, which goes to 0 as k goes to 0. And so in that sense, this is a weak cross-section, okay? The natural scale in the problem is k, that's the wavelength of my experiment, and as k goes to 0, this dimensionless cross-section, which I can compare to 1 to see if it's big or small, goes to 0. But if A goes to infinity, plus or minus infinity, then our scattering amplitude, 4 pi over m, 1 over, and then I have 1/2 r naught k squared plus dot, 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 because the scattering length is 0, sorry, minus 1 over A goes to 0, plus minus ik. And so now you see that this dominates at low k in the denominator. And so A squared goes like 4 pi over m k squared, and sigma hat equals order 1. And so we have a strong cross section. And so what we see then is that for a generic theory, we have an irrelevant interaction. The physics is small in the IR. This is the case for Fehmery's theory, for example, where the cross-section for neutrino-neutrino scattering goes to 0 at low K, which is why we call it the weak interactions, even though if we did our experiment at 100 Jeb, it wouldn't look weak at all. However, we find that it is not necessarily irrelevant, because if I fine-tune the UV theory, I can change it to be called a marginal interaction, namely one where I get a cross-section of order 1. So fine-tuning so what looks naively like an irrelevant interaction it can make a naively irrelevant interaction look relevant, or something else we'll talk about later, which is marginal, but important in the IR. And the fine-tuning is, in this case, one of these values. So particular values of coupling can make the cross-section important in the IR. If you're not exactly at one of those points, at sufficiently small k, this IK will always dominate. Because when k gets less than 1 over a, sorry, I take that back. Yeah, so I'm sorry, I said it the wrong way. That if you're not exactly at this fixed point, then for small enough k, this IK becomes less important than the minus 1 over a. And you'll always end up in a situation where you've got k squared, a squared here, which goes to 0. So you have to be exactly at one of these points if you want the interaction to be important all the way down to k equals 0. So this is an example of a critical point in a renormalization group language. Now, let's put some of this to use. Well, let's first look at the EFT. At first, this looks like a terrible idea. I can't solve the Schrodinger equation with the delta function in 3D. And furthermore, the delta function looks like a square well that's really, really narrow. And we just decided that cross sections always go to 0, like k squared over lambda squared. And here, you might think a delta function is a square where lambda goes to infinity. I take the width to 0, okay? So it looks like this would be always irrelevant. And that is true. For a generic coupling, the delta function has no effect on scattering at low energy. So how in the world is this effective field theory going to reproduce scattering from a finite size square well? Well, as I take the width smaller and smaller, I'm going to have to fine tune the coupling to one of these critical points in order to have some residual interaction show up at low energy. So this is how Wilson taught people to do lattice field theory. They said you have to, as you take the lattice space into 0, you have to tune it to a critical point, to a phase transition. And the language of phase transitions makes it much easier to understand than this case, which is that in a lattice theory, you want to have the lattice spacing tiny, and you want your particles to have long wavelengths because you want to describe the physical length scale, which is much, much bigger than the lattice spacing. And he said, this looks like a condensed matter system. What type of condensed matter systems have correlations over very long wavelengths compared to the lattice spacing? And the answer is a condensed matter system that's tuned to a second order phase transition. And so Wilson's view of how to do quantum field theory on the lattice was very similar to our result here, namely that you have to fine tune interactions if you want to take the cutoff to 0. Okay, so we're now going to look at an effective field theory where I've got this I dagger I dt minus del squared over 2 plus del squared over 2m psi, and contact interaction, which will be minus C naught over 4 psi psi dagger psi psi. And this is all at the same space-time point. And C naught is going to therefore look like our coupling constant because you can see from this Lagrangian, just from the Feynman diagram, the Feynman diagram for this, the Feynman rule for this interaction is that this is minus I C naught, the common torques for a psi dagger squared and a psi squared canceled before, and you get a minus I C naught, and therefore this Feynman diagram shows you that these particles have to sit at the exact same space-time point if they are to interact, and that is the definition of a delta function. Now, the nice thing is that when we stick this interaction into our Lippmann-Schwinger equation, those ladder diagrams become very simple. We have that I times our scattering amplitude is equal to the sum of diagrams like that. And this is equal to minus I C naught times 1 for the first diagram plus B C naught, this second diagram, where this extra C naught is from the next coupling, and B is going to be the loop with the minus I from the vertex. Put in. So B is this diagram there with no coupling constants at the ends. Empty hole here. I've taken out the C naughts explicitly, so there are no C naught factors in that diagram. And in this case, I can sum this all up, of course. I get that this is equal to minus I C naught over 1 minus B C naught, which is equal to, I'll write this as I times minus 1 over C naught plus B. And so if I want to calculate the scattering amplitude, all I have to do is a single one-loop diagram. So the kinematics are the following. I've got, I'm going to take, I'll do it here, sorry. So I'm going to have E over 2 and the momentum K coming in this way, and E over 2 and momentum minus K going this way, and then coming out, I've got E over 2 K prime, but I'm going to be looking at S wave, so I won't care about the direction. And so K squared equals E.
B is some function of K square, K, right?
A factor of what?
B. B is some function of K, right? The
so
loop,
so
the B.
There are no, I'm sorry.
That diagram, that B equals to
B,
minus.
This B is a function of the energy.
Okay.
Yeah. So this B is equal to, there's a minus I, and then we have an integral EQ0 over 2 pi. So I'm going to put a loop integral Q there, integral D3Q vector over 2 pi cubed. And then I have an I E over 2 plus Q0 minus Q squared over 2m plus I epsilon. And then I have a second propagator, which is equal to I over E over 2. And then because the Q is now going against the arrow, I have a minus Q0 here. And then minus Q squared over 2m plus I epsilon. So I have to do this diagram. And so the first thing to do is do the Q integral. The I that you get from the Cauchy's rule cancels the minus I, and the 2 pi from Cauchy's rule cancels this 2 pi. I'm left with this integral, and somehow there's a minus sign. I don't remember why. You end up getting this, and it doesn't matter which way you close the contour, because you either pick up the pole from this propagator or from that propagator, and you get the same answer whichever way you close the contour. So this looks familiar. This looks like the propagator for a non-relativistic particle with reduced mass m over 2. Normally you'd expect twice the mass here, but reduced mass is what comes in, which is m over 2. So twice m over 2. Now we see a problem, which is that this is d3q, but the propagator falls off like 1 over q squared. So this is linearly divergent. So we have to do something to regulate it. If we do a momentum cutoff, we get that this is equal to minus m lambda over 2 pi squared minus I m k over 4 pi plus order 1 over lambda. So this is the linear divergence. This is the non-analytic piece that we expect from the fact that those two particles could have been on shell. Root of ME. And then stuff that goes away as lambda goes to infinity. So we stick this in to our formula over here. And we get, I'll cancel out the i's. A is equal to 1 over minus 1 over C naught minus m lambda over 4 pi minus I m over 4 pi k plus order 1 over lambda. So far, I have done the first step, which is to regulate the theory by putting in a cutoff. Now I have to renormalize. I'm going to declare that minus 1 over C naught plus m lambda over 4 pi is defined to be 1 over C naught, sorry, minus 1 over C naught normalized. Yeah, 2 pi squared. Okay, now this is scheme dependent. When you renormalize, you have to absorb the thing that'll blow up. But you can always add any finite amount you want, as long as it's analytic in fact, it could be even K dependent. As long as it's analytic in K, That would correspond to shifting some other couplings in the effective field theory. But my choice here of just taking off this infinite part is a choice of scheme, okay? It works, it makes it finite, but it's not the unique way of making it finite. So somebody else could say, I also want to subtract off something that goes like minus 1/3 m squared. That's a different scheme, works fine. Okay, so then what you find is that A be written as 4 pi over m, 1 over minus 4 pi over m c naught renormalized minus ik, and this, of course, equals 4 pi over m, 1 over e cotangent, k cotangent delta minus ik. So you can see that this effective field theory has replaced k cotangent delta with a much simpler thing, which is a constant, which can only work at low k. It tells you that 1 over a is equal to 4 pi over m c naught renormalized, or c naught renormalized is the matching condition for c naught renormalized is 4 pi a over m. This is our matching condition because presumably experimentalists have measured phase shifts, theorists have extracted from that the scattering length, and therefore this is experimental data that you got from scattering off this square well, which is a tiny square well. And so I'm fitting C naught renormalized to that, and that's my renormalization condition. And I now can take lambda goes to infinity because the air coupling has to change, of course, but C naught renormalized is held fixed to the data. Now, notice that as lambda goes to infinity, C naught has to be fine-tuned to a particular value. That is exactly the fine-tuning that we predicted by looking at what happens with square wells as you make them smaller and smaller. If you want to have any effect of low energy, you better fine-tune the coupling to a particular value. And in this scheme, this is the value that it has to be fine-tuned to. So almost exactly to this value, but a little bit off by the experimental data. Question? Yeah.
In case of a relativistic theory, I would have expected a branch cut instead of a pole for this loop kind of contributions.
One more time.
For the relativistic theory, I would have expected a branch cut for this loop integration instead of a pole, right?
So this K is a branch cut. It's a square root of E.
Okay.
That's exactly the branch cut you would expect, and you're correct. When you have two particles that can go on shell, you get a branch cut. You don't get a pole. So at this point, it's useful to do some dimensional scaling arguments to summarize some of the things we've observed in the 1 and 3-dimensional case. So you're used to relativistic scaling, probably, if you've taken quantum field theory. We set H bar equals C equals 1, and then you can define, we can say that I take X goes to X over S, and T goes to T over S. They scale the same way because that's what we do in relativistic theories. And then we say that the action goes to itself. It doesn't scale at all. So we're looking for a scaling symmetry in our theory. And so if we write the action is equal to integral dt dx of psi dagger I dt plus del squared over 2m psi minus c naught over 4 psi dagger psi. Then you see then that this, so I'll come up with a, we'll say that X has mass dimension -1. It scales like S to the -1, which we can write as X equals -1 and T in square brackets is -1. So that means it has dimension inverse mass. And therefore, this has dimension D plus 1 minus D plus 1, sorry. And this has dimension 1, and this has dimension 2. And since we're adding these two things, they have to have the same scaling dimension, which means that we must have the mass has dimension 1. So we have to add in mass equals 1. We want the action to be invariant. And then, because this quantity here is the mass dimension 1, this has the mass dimension minus D minus 1, we must have then that psi dagger psi must have dimension D, or psi has dimension D over 2. So 3 halves when capital D is 3. And then this has dimension 2D. And therefore, C naught, this is 2D minus D minus 1. C naught must have dimension 1 minus D. So for example, in D equals 3, we get C naught is equal to -2. And that is the mass dimension of G Fermi, for example. This D equals 1, we get C naught equals 0. This is not useful scaling for a non-relativistic theory, though, because in a non-relativistic theory, this M is nothing we can, it's a huge scale. It's not a small scale, okay? So it's something fixed. We can never change it. So in a non-relativistic scaling, we don't scale M. It's a fixed relationship between space and time, if you want. We take M equals 0. Then if we take X equals -1, you see from the kinetic term, if this now has dimension 2 and M doesn't scale, then this must also have dimension 2. So we must take that T has dimension -2. And then this has dimension -D minus 2. And because this is dimension 2, and this is -D minus 2, we still have that psi equals D over 2, as before. But when we look at C naught over 4, psi dagger psi squared, this has dimension 2D as before, but now we've got a -D minus 2 here, and so that we find that C naught is equal to D minus, has dimension D minus 2. And this is a useful scaling because if D equals 3, we see C naught has dimension 1. sorry, this is 2 minus D. C naught has dimension -1, and in D equals 1, C naught has dimension +1. Okay, and this is the hallmark of an irrelevant interaction. It's got negative scaling dimension. And this is a relevant one. You don't see that in the relativistic scaling. Furthermore, it's no accident that because this is -1, the divergence that we encountered here was linear, lambda to the +1. They go hand in hand. The more irrelevant an interaction, the more divergent the diagrams that renormalize it. And the power is actually closely related to the scaling dimension.
What is the argument? You don't scale it.
See?
For NR scaling, what is the argument behind you do not scale M?
It's basically because we don't use the same units for space and time in a non-relativistic theory. There's no reason to. And M is basically a conversion. It's a unit conversion in that language. It's not something that we rescale at all. It's a property of nature that just comes down to us with a nucleon. We can never change it. Yeah. So the fact that we're integrating something that's linear in E and quadratic in Q means that the poles here occur at E proportional to Q squared. And so if you want to stay in the pole, you want to scale E and Q squared the same way. While in a relativistic dispersion relation, it'd be E squared and Q squared that would scale the same way. I'm sorry?
Non-relativistic scaling or natural units like H bar equals to C equals to 1, this thing?
I'm not following, sorry.
The H bar, yeah, and I wanted to ask, are you working this natural unit for this non-relativistic scattering?
He has put H bar equals to 1.
Yeah. But I'm not setting C equals 1, if you want. C is absorbed in M. And
C should actually never appear. C, you should be able to take C to infinity in this non-relativistic theory, right?
okay, so so you can use the scaling to look at the properties of our sigma hat. Okay, sigma hat is supposed to be scale invariant. C naught squared. Well, if you're going to make it scale invariant in the case where C naught is -1, you're going to have to put a K squared here, which again tells us it's irrelevant as K goes to 0. And sigma hat proportional to C naught squared, and D equals 1. Well, C naught is +1, so you have to put a 1 over K squared. And so we find that things blow up. Now, and that's the 1 over K squared stuff we found in the reflection coefficient in the, which set R to 1. So this has the scaling, helps you understand the effect of, well, I should say something here, that when I say sigma hat is proportional to C naught squared, I'm doing a Born approximation. This says if I did a Born approximation, I would see the cross-section blow up as K goes to 0. But of course, if the effective C is really C over K, that tells you the Born approximation will always break down in the infrared limit. So you have to do non-perturbative calculation if you want to understand reflection off a delta function in 1 dimension. If you looked at QCD in 2 + 1 dimensions, and you asked what's the dimension of the Kaplan constant, you find it has positive mass dimension, just like C naught in the 1-dimensional square well. And therefore, you reach immediately the same conclusions that if I did a Born approximation, the cross-section would blow up in the infrared, which means that the theory has to become non-perturbative. And so QCD in 2+1 has a scale which where the theory gets strong, just that follows immediately from its dimension. If you did QCD in 5 dimensions, G would have negative mass dimension. It's irrelevant. You'd find there's no scattering in the infrared. You try to understand gauge theories in 5 dimensions. So let's try to apply this now, and this will be an introduction to what Daniel will be talking about, namely using this type of setup. See, when you include a physical pion, you're going to start getting cuts that are related to m pi over 2. And so a derivative expansion for the low energy theory will never be able to have a radius of convergence beyond where the non-analyticity comes in. So the way effective field theory deals with that is you can now add light particles to take into account that non-analyticity, and the rest of the stuff still has a good derivative expansion to a higher scale. And so if you add the pion explicitly, you should be able to go on beyond k equals m pi. But I'm going to just be sticking to k below m pi, and then everything should be described by contact interactions because there are no light hadrons below the pion. So what is the goal? Okay, up to now I just showed you can get sort of the same answer, but the difference between what we've been talking about so far is where I had a model for exactly what's going on, square well or something. It's the exact answer. With nuclear physics, we don't know exactly what's going on. It's very complicated. These are composite objects of quarks. They exchange resonances. They've got all sorts of excitations, mesons. So what we do is we look at the low energy physics, and we'll do, in the effective field theory approach, we'll put in all these local operators in a derivative expansion, and then we have to find a way of systematizing it so that we can compute our answers in a momentum expansion. So if I ever write an email mentioning the word pionless EFT, my spell checker changes it to pointless EFT, which fits the opinion of many nuclear physicists. So the first thing is you write down a Lagrangian. We don't know a lot about QCD, but we do know something about its symmetries. So we have to impose all the same symmetries that the high energy theory has, like charge conjugation invariance and CP invariance, so on. Lorentz invariance, obviously. And then what we do is we have to come up with a power counting scheme. Which operators enter at which order? For weak interactions, that's pretty simple. You do a scaling argument. You look at the scaling property of all the coefficients of the operators, and that tells you how many powers of k they'll have to involve when you compute your amplitude. But if you have a strongly coupled theory where for some unknown reason, the UV physics has been fine-tuned, then all bets are off. You won't be able to guess what the scaling is. You'll have to do some more careful work. And that is, interestingly enough, the situation in the real world. The neutron-proton scattering length in the 1s channel is something like 23 Fermis, which is many, many times the Compton wavelength of a pion. And that's really weird and unnatural. In the 3s1, it's slightly less fine-tuned, but still, the deuteron binding energy is 2.2 MeV, which is very small. Once I got a letter from Steve Weinberg saying, David, do you understand why the deuteron is so weakly bound? I had to answer, no, I don't. But I had this letter from Weinberg with a physics question with his signature on it. And I proudly put it on my bulletin board, and then I forgot about it. And then I looked back at it a year later, and the sun had completely erased the signature. I was so sad. Then finally, you compute whatever process you're interested in. And then comes the most important part of the EFT. You can estimate your error because you stopped at some finite order in the expansion. So if you stopped at order k to the 6 over lambda to the 6, then the new correction will be k to the 8th over lambda to the 8th. But do you know what lambda is? Well, what you can do is you can plot on a log-log plot your error versus your momentum. And so if you do a lowest order calculation, so you know what the physical data is for something, and you know what the lowest order prediction is. So for example, you know the true scattering phase shift as a function of k, and your lowest order fit the scattering length. So your phase shift is going to be off in the effective theory because all you got right was the scattering length. You didn't get the rest of it. So you'll have some error on a log-log plot. If you really do have a power law error, then you'll get something like that. Goes up on a log-log plot. And then if you do, this is your lowest order. If you do your next lowest order, you should get something that looks like this. It converges. This dependence on k is steeper because you have a higher power of k dependence, which on a log-log plot means a steeper slope. And then you do your N3LO, and hopefully, or N2LO, they sort of cross somewhere. And then this is basically your log lambda. So you might have some guess where the theory should converge, but it's only after you can compute several orders and compare with the data that you'll be able to get a good feel for whether you've got a good expansion or not. So if you have lines that don't get steeper, you're not doing a good expansion. Or if they don't converge, if they converge at really low scale, it means your expansion's working less well than you thought it would. So there are ways of checking. And then you can have some sort of error analysis along with your prediction, which is crucial for doing good science. And a beautiful example of the value of effective field theory is if you look at the Phillips plot, and unfortunately I didn't get a copy with me. If you plot the triton binding energy versus the neutron-deuteron scattering length, and prior to effective field theory, what people would do is they would come up with what they think were good potentials to describe nucleon-nucleon interactions. And they fitted against lots of data. But these potentials were all very different, and what went into them was very different. And if you plot the predictions from different potential models, it was noticed by Phillips, not Daniel Phillips, in 1968, that they sort of lay on a line. And so this is curious. First of all, it's sad that they're not all on the same point. It means that you don't know, you can't trust your models because they don't agree with each other, okay? But it's also weird that they formed a line rather than just some scatter, okay? But when effective field theory comes along, what you find is that when people looked at three-body scattering and used a potential model built on two-body potentials, if you had an interaction like this, and you, depending on how you dealt with the high momentum stuff, this looks like a three-body interaction. Okay, and each different potential model with a different regularization scheme or dealing with infinities and so on comes up with a different value for that, okay? And now what you find in effective field theory is that this operator comes in at the same order as the two-body stuff, and therefore you have to fix it to data. If you don't fix it, your prediction will lie on a line depending on what value you take for that, okay? So if you come up with random values for this, you'll lie on some line, okay? But when you fix it to data, you can get very close to the true answer, which is somewhere around there. And so this was a beautiful confirmation of the power of effective field theory, that the power counting told you that there was an operator like this that came in at the same order as the two-body scattering. It was missed by potential models. And potential model had no systematic way of seeing that this is missing. People might throw in new models with new three-body interactions. Some of them might put the right one in, some they put the wrong ones in, and you can't tell what you're doing. So that is the value of the effective field theory approach. And so the procedure then is you take some data and you fit your constants. If that was the whole story, it'd be really boring because you took some data and you approximated it, okay? But the value of the effective field theory is then you can use those same constants in other processes, such as you could put the photon in and start using the couplings that you computed in the scattering data to compute electromagnetic form factors or NP to D gamma cross-section or something like that. And so it's a predictive theory because there are more processes than there are low energy constants. So for the pineless EFT, we're going to have to deal with the fact that the real world is fine-tuned and our naive power counting scheme is probably not going to work, because if it did work, we'd immediately conclude that nuclear-nucleon scattering was irrelevant, which would be at variance with our experience in the real world. So what we're going to do then is I'm going to ignore isospin for now. So I'll just take my nucleons to be spin half fermions of one flavor. We write our Lagrangian as n dagger I dt plus del squared over psi at n. But then we put in our C naught over 4 n dagger n squared. And we'll go farther. Where this is not going to be important for my lecture, but this is del going this way squared, twice del going this way, dot del going this way, plus del going this way squared. You need combinations of derivatives that leave this thing Galilean invariant, because Galilean invariance is a symmetry of QCD, and so the derivatives have to go in certain combinations if they're going to appear without time derivatives. But that's not relevant for this talk. Now, the other thing we're going to do, though, is to simplify the calculations. Momentum cutoffs are really hard to work with, and they can be misleading. So we're going to do dimensional regularization. So you put a mu over 2 to the 4 minus d out in front, where mu is a fictitious scale. Mass scale. And it's chosen to make the Lagrangian dimensionless even when I go to different dimensions. So I'm not going to derive the power here. It's not going to be too important, and I want to keep going. So we have that our scattering amplitude, as before, is equal to 4 pi over m, 1 over p, k cotangent delta minus ik. And we can imagine expanding this to higher order than the usual. So I'll write this as 1/2 lambda squared times sum on n Rn k squared over lambda squared to the nth plus 1. So the first term would just be 1/2 R naught k squared, which is the effective range, but I'll say higher order terms in that expansion. And so if I expanded A, what would I get? Powers of k, it's not analytic. I would get 4 pi a over m minus that times 1 minus I a k plus a r naught over 2 minus a squared k squared plus order p cubed over lambda cubed. So this would be the generic expansion you would expect if you expanded this in powers of k. Now, if we had a generic UV potential range 1 over lambda in the same sense that I mentioned earlier, that the potential is confined to a spatial size of about 1 over lambda. And as generic and not especially weakly coupled, then you'd find that everything would have normal, so it would be set by, all the dimensional quantities would be set by lambda, and you would expect A would go like 1 over lambda, R naught would go like 1 over lambda, R1, see the way I've defined it, R1 is also dimension of length. And then you see that all these terms are just powers k over lambda squared, k over lambda cubed, and so on. So a simple Taylor expansion would be pretty accurate with a radius of convergence on the order of . So this is a very easy theory to deal with in an effective field theory. Our tree level scattering, including all infinite number of scattering terms, is equal to minus I u over 2 to the 4 minus d times sum on n equals 0 to infinity c2n p to the 2n, k to the 2n. Just have to trust that I normalized each operator such that all the combinatoric factors were canceled out. And that's fine because I haven't told you what the C's are. So this is my tree level diagram, including all operators. Then we have to compute the bubble diagrams. Let's look at the type of integral we're going to have to face when we look at the single bubble. So we take I mu over 2 to the 4 minus d times the integral dq over 2 pi to the d times q vector to the 2n magnitude over e over 2 plus q naught minus q vector squared over 2m plus I epsilon. E over 2 minus q naught minus q squared over 2m plus I epsilon. And we compute this using dimensional regularization. And dimensional regularization is a very strange beast that throws out all power law divergences as if they didn't exist. Okay, so if you do something which is quadratically divergent, you'll never see it in dimensional regularization. So there's a hidden subtraction scheme going on, which just gets rid of power law divergences. Because of that, q squared upstairs, I can write that as q squared minus me plus me. This part will end up canceling one of the propagators. Well, I should have done the Q0 integral first, so make it easier to see. So this is equal to u over 2 to the 4 minus d times integral d minus 1 q over 2 pi to the d minus 1 times u to the 2n over e minus q squared over m plus I epsilon. And so if I replace a power of q squared by q squared minus me plus me, then the q squared minus me cancels the propagator. I'm left with the q squared to the 2n minus 1, but that's the divergent integral, but in dim reg it's 0. So everywhere this contribution goes away, so I can ignore that and I can replace q squared by its on-shell value, which is me. So therefore, this is equal to u over 2 to the 4 minus d me to the 2n times our familiar diagram that we already did with the momentum cutoff. Which is that. And if you compute that, then this is equal to minus m times me to the n. Sorry, this is to the n, not 2n. Times minus me minus I epsilon to the d minus 3 over 2 times a gamma function of 3 minus d over 2 times u over 2 to the 4 minus d over 4 pi to the d minus 1 over 2. So that's what you get in dimensional regularization. And the beauty of it, the fact that these q squares all come out, means that we're going to be able to sum this infinite sum as a geometric series just as before. A big question, though, is what happens as I take d goes to 4? Well, this gamma function doesn't have a pole at d equals 4 because this was a linearly divergent integral, and dim reg doesn't see linear divergences. So there's nothing wrong with taking d goes to 4. We can ignore mu. So this is what we call minimal subtraction. We get me to the nth m over 4 pi times the square root of minus me minus I epsilon, and this is what we call ik. This is equal to k to the 2n m over 2 pi times minus ik. And so your amplitude is minus sum on n C2n k to the 2n over 1 plus I mk over 4 pi times sum on n C2n k to the 2n. And so if I do a Taylor expansion, just like we did over there for the generic case, we get A0, the leading order term, is minus C naught. A1 is equal to I C naught M over C naught squared, M over 4 pi times K. A2 is equal to C naught cubed MK over 4 pi squared minus C2 K squared, and so on. And so you can equate these things here with this expansion here. And you see that there's a one-to-one correspondence between all the C's and all the effective range parameters, but you have to work a little bit to get them. You find that C naught, we're now going to match, assuming that the effective range parameters have been experimentally determined. You get C naught is equal to 4 pi A over M. C2 equals C naught times A R naught over 2. And C2n goes like, all of them go like 4 pi over M lambda, 1 over lambda to the 2n for generic potential, namely the one where there's no huge scattering. So we have a perfectly good expansion. We see that we take the fact then that we take it just the naive dimensional scaling of the operator. If it's got two derivatives, it goes like k squared. If we want to expand something to order k, if we want to expand the amplitude to order k squared, we have to put it in linearly. And there's a clear rule at what order we need to include what coupling. So that is where I have to leave it today. And while this is very simple and sort of trivial, it's not the way the world works because the scattering length in nuclear physics is large, so we'll have to come up with a different power counting scheme. And that's what I'll start on at the beginning of the next lecture. Questions?
Vertices like N-dagger and whole cube kind of interaction.
One more time.
The 6-point vertices like the N-dagger and whole cube kind of.
What we'll find is that there'll be, what we will find is that when we define C naught hat equals C naught mu, we'll find that this obeys a RG equation. So it looks something like this. This is the beta function. And there's a fixed point at 0, which is the trivial case. That's the naive case we were talking about now. So if you set C naught goes to 0, everything comes, C naught's weak. And then there's a non-trivial one at -1, and that's going to correspond to the infinite scattering length case. And it's unstable.
He's asking about 6-point vertex, N dagger N cube.
Say it again?
N dagger N cube. So you have N dagger N square.
Yeah. Oh, yeah. So
So N dagger.
yes, if you want to talk about three-body physics,
Yeah,
then you have to include those, and those are going to be outside the scope of my lectures. Okay, I'm going to be talking more about the effective field theory.
But via loops it can
I'm
continue
sorry.
to.
Oh, I'm sorry. So then what happens is then what you find is that when you include all diagrams like that for three-body scattering. You find that you get an integral equation that you can't renormalize, it's infinite, unless you include a three-body counter term.
Two loops and the 2 6 points giving us 4 points.
No, sorry. What your diagram is. You want to know whether there's a divergent for particle?
He wants you to, so this would be possible if you had antiparticles in the theory, right? But particle number is conserved in this theory. So if you start with 3 particles, you have to end with 3 particles. Does that answer your question? No? So if you start with, okay. You can't, particle number is conserved in this theory.
You want this diagram or?
No, he wants to create a particle for the intermediate state.
I'm sorry?
He wants to create a virtual particle for the intermediate state.
That's actually something I've been working on recently called a dimer, where you have virtual particles living in with barrier number 2 or higher. Is that what you're talking about?